Hello everyone. Today, I'm going to introduce a fascinating topic, how we use transformer models to generate expressive piano music. Let's dive into the details. Music transformer is a neural network developed by Magenta. Unlike traditional methods, it doesn't just create a score, it directly generates expressive performances. This allows for greater coherence and musicality in the compositions. The model has three standout features. 1. Event-based representation. It skips the scoring step and focuses on creating performance-level output. 2. Relative attention. This mechanism ensures the model can detect and replicate musical patterns effectively. 3. Longer sequences. It can handle much longer pieces of music compared to older models. Music transformer is highly versatile. It can generate original music from scratch. It can also continue a given melody, making it a helpful tool for composers seeking inspiration. Another important framework is Wave-to-MIDI two-wave. It converts audio to MIDI, uses a transformer to generate new music, and converts the MIDI back into audio. This ensures high-quality music generation. For our dataset, we partnered with organizers of the International Piano E competition for the raw data used in this dataset. The dataset contains about 200 hours of paired audio and MIDI recordings from 10 years of International Piano E competition. Audio and MIDI files are aligned with 3 milliseconds accuracy and sliced to individual musical pieces, which are annotated with composer, title, and year of performance. A train validation test split configuration is also proposed, so that the same composition, even if performed by multiple contestants, does not appear in multiple subsets. Repertoire is mostly classical, including composers from the 17th to early 20th century. Before training, we 1. Split the data into training and validation sets. 2. Converted MIDI files to audio for preview. 3. Tokenized the MIDI data for model input. Our model builds on the music transformer architecture, incorporating a custom decoder with relative attention, a loss function tailored to handle music tokens. The dataset is divided into training and validation sets to ensure the model learns effectively and is tested accurately. Tools like FluidSynth and PrettyMIDI are used to convert MIDI files into audio for previewing the data. Before training, MIDI files are tokenized into sequences of musical events. Tokenization translates raw MIDI data into a format the model can process, encoding details like notes, durations, and dynamics. Tokenization ensures that the model understands the structure and meaning of musical data, which is critical for generating high-quality music. Dataset objects are created to yield batches of input and target sequences for training. These batches are essential for efficient and scalable model training. Structured datasets ensure consistent data flow into the model, facilitating optimization during training. The music transformer uses a custom decoder layer with a relative global attention mechanism. This mechanism improves the model's ability to understand relationships between musical events over long sequences. It is time to define the model architecture. We use a transformer decoder architecture with a custom attention mechanism, relative global attention. It is used in place of the standard multi-head attention layer in the transformer decoder. The main difference is that it includes a relative positional encoding that allows the model to learn relative positional information between tokens. The decoder layer is a critical component, composed of multiple custom blocks designed for advanced music generation. Each block utilizes the relative global attention mechanism, capturing intricate patterns within sequences. Additionally, An embedding layer translates tokenized inputs into a rich representation, enabling the model to interpret and generate music with remarkable detail and depth. This architecture ensures that every layer contributes to a harmonious blend of precision and creativity in the final output. The decoder architecture is built from a stack of decoder layers, each leveraging the relative global attention mechanism for enhanced pattern recognition. This structure also includes an embedding layer that transforms tokenized musical inputs into dense vector representations, creating a foundation for expressive output. Together, these components enable the model to interpret complex musical data and produce coherent, intricate compositions that align with the intended artistic vision. With the defined decoder layers, the music transformer decoder model takes shape. It processes the embedded input through the stacked decoder layers and applies a final linear transformation to produce logits for each token. These logits represent the likelihood of specific musical events, enabling precise sequence generation. This architecture allows the model to seamlessly convert learned representations into expressive and coherent music, bridging the gap between technical structure and artistic creativity. The training process incorporates a custom loss function tailored for music generation. This function calculates categorical cross-entropy loss, focusing solely on non-padding tokens to optimize learning. Additionally, we implement an adapted exponential decay learning rate schedule, which adjusts dynamically based on the embedding dimensions. Together, these innovations ensure efficient and precise training, allowing the model to refine its understanding of musical structures and deliver high-quality compositions. The model training process begins with defining a training function that compiles the music transformer, sets the appropriate parameters, and manages checkpoints. Checkpoints save the best-performing model states, allowing seamless resumption and further optimization. By leveraging the Maestro dataset, the training refines the model's ability to generate expressive and coherent music, ensuring continuous improvement and adaptability throughout the training cycle. The model's training is powered by a robust framework that allows for checkpointing and iterative improvements. After defining the training function, the model is compiled and optimized for generating high-quality music. Checkpoints ensure that the best version of the model is preserved, enabling fine-tuning or resumption without losing progress. This process enhances the model's ability to deliver accurate and expressive musical outputs, pushing the boundaries of AI-driven creativity. With the trained model, we can now generate music by using a seed MIDI file to kickstart the process. The model extends the seed with coherent, expressive sequences, creating entirely new compositions while preserving the original musical context. This approach showcases the model's ability to blend learned patterns with creative generation, delivering outputs that feel both innovative and musically authentic. The trained model enables the generation of original music sequences by taking an existing MIDI file as a starting point. It uses this seed to produce extended compositions that maintain coherence and musicality. This capability highlights the model's strength in blending pre-existing motifs with creative improvisation, making it a powerful tool for composers and music enthusiasts seeking fresh and inspiring ideas. Experimental results demonstrate the model's ability to generate coherent and expressive music, improving with each training epoch. By fine-tuning parameters and utilizing advanced attention mechanisms, the model balances creativity and structure. These results highlight the transformative potential of AI in music composition, paving the way for innovative applications in creative industries. project showcases the successful implementation of a custom transformer decoder for music generation, inspired by Huang et al. 2018. Key achievements include defining a unique loss function, optimizing the learning rate schedule, and pre-processing MIDI files for effective training. After leveraging the Maestro dataset, the model generated expressive compositions. Future enhancements, such as refining models, using professional seed sequences, and applying post-processing, will further elevate the quality of AI-generated music. The journey toward mastering AI-driven music generation is an ongoing process. Each step brings new insights and opportunities for innovation. By refining models, exploring advanced techniques, and embracing creativity, we move closer to realizing the full potential of AI in music composition. The path is challenging but filled with the promise of transforming the future of music. Thanks for your listening.